We want to look now at another way of graphing curves, specifically using parametric equations instead of the standard x with respect to y kind of an equation. So a parametric equation means that our points on our grid, x, y, are defined through a third variable. Commonly t is what we use, and t is called the parameter. So here is an example of a set of parametric equations where the x-coordinate is defined as a function of t and the y-coordinate is defined as a function of t. And in this case we're going to use t to be all real numbers, but we can restrict our parameter. I kind of like to think of t as time going on. So what I'm going to do here is create some points for the curve represented by these parametric equations. And so all I do is take some sample points for t, and I'm going to take them in the order of smallest to largest, and plug them into our two equations to get the corresponding x and y coordinates on the graph. So if I plug -2 in, -2 squared is 4, minus 2 times -2 is 4, so that becomes 8. And the y coordinate, I plug t into the other parametric equation, and I get -3. So 8, -3 is the first point I'm graphing on this grid, and then -1, and so on. So I'm just going to create the points from that. I'm going to get 3 and -2 for y. If I plug in 0, the x-coordinate will be 0. If I plug in 0 to this, it would be -1. Plug in 1, I get -1 and 0. If I plug in 2, 2 squared is 4, minus 4 is 0. And for y, I get 1. So I can see that I'm getting a non-function. You often get a broader range of graphs from parametric equations than you can from standard Cartesian equations. Alright, continuing on, putting in 3, we get 3, 2, and for 4 we get 8, 3. So put those points on the grid, graph. Looks like we're getting a sideways parabola. Alright, so just to review what we've talked about so far. So parametric equations are where x and y are defined in terms of a third variable. X is a function of t and y is a function of t. Parametric equations are often used to represent the movement of a particle in the xy plane. Alright, so I was talking about the order in which I was graphing from smallest value of t to largest. As I was graphing, the points were being plotted this way, this one, then this one, then this one. And so, because parametric equations are used to represent the motion of a particle usually, we often show the direction of graphing from smallest parameter to largest through arrows on the graph. Right? So parametric equations produce curves, commonly called parametric curves or trajectories. And as I said, t is what we call the parameter. So I mentioned at the beginning that often we restrict the domain of our parameter. So if I take the same set of equations I had above, here we are, and I say t can only go between 0 and 2, then I'm restricted to graphing corresponding x and y points that are produced between t values of 0 and 2. And on the grid, that would be from here, showing it in green, going all the way to here. Okay, this would be called the starting point, and this would be called the terminal point. Originally, when I was graphing t with all real numbers, there was no starting or ending point because all real numbers were being used. All right, so initial point and terminal point. Now, you can graph parametric equations on your calculator, so let's just look at that. So the first thing you need to do is go to your mode button, and on the 5th line down, I think it is, instead of in function mode, sort of Cartesian mode, let's go to parametric. All right, and if we now go to y equals, we'll see that we can enter our pairs of equations. X is a function of t and y is a function of t. So I'm going to do that, and when I press the x button or the variable button, I now get t's, t squared minus 2t. And for the y equation, it's t minus 1. All right, with my window dimensions, since I was doing t as all real numbers, I'm going to take t values from -10 to 10. Now the t-step, this is the default number for t-step, and t-step is sort of how often the calculator recalculates the x and y points for a given value of t. So if it uses one value of t, the next value of t that it will use to calculate points is 0.13 units later. All right. So the higher this number is, the less accurate your graph will be, the less smooth it will be. The smaller it is, the more points the calculator is going to graph, but it may actually slow your calculator down. So this is a good number to sort of default it at. You can experiment with making this number higher and lower and see what happens. All right, so we got our range for t set. Now our x, I'm just going to set this similar to the graph I have here. I'm going to go from -2 to 10. And markings of 1 is good. And here I'm going to go from -4 up to 5. Now as a graph, you'll know that it'll graph in the same orientation as the arrow. So starting from this point and going in this direction. And you can trace, and it'll give you, for a given value of t, it will give you the corresponding coordinates. And you can go to your table and see your t, your x, and your y. Now, let's just change our range for t in this example that I did below, where I only wanted part of the graph to show. And so my t minimum was 0 up to 2. And you'll now see how the graph changes. We just get that part. Okay, something else we can sometimes do is we can express our parametric functions in terms of our traditional Cartesian equation form. And so that's what I want to do here. Take the equations I've just been dealing with and write that as x in terms of y. All right, so the key to this is if you isolate t in one of the equations, so I'm going to do that here, t is y plus 1. You can then, in your equation for x, wherever you see t, replace y plus 1 for t. And now you're getting your Cartesian form equation with x related to y. Let's work that out. And if I simplify that, I'm going to get x plus 1 equals y squared. And I'm going to leave it like that because I know that x equals y squared is the inverse of y equals x squared. So that's a sideways parabola which has been shifted 1 to the left, which is exactly what I have graphed. All right, here's another example. We want to graph the parametric curve represented by this set of parametric equations. X is cos t and y is sine t. And we want to use values of t between 0 and 2 pi. So we can just begin by taking some sample points. When t is 0, the cosine of 0 will be our x value. That'll be 1. And for y, it'll be sine of 0, which is 0. All right, so we can keep taking points. And I'm going to take pi over 6, which is 30 degrees. And for x, the cosine of pi over 6 would be root 3 over 2, which is 0.86, 87 rounded. And the sine of pi over 6 is 0.5. And then I'm going to take 30 degrees more, which is pi over 3 radians. And the cosine of that would be 0.5. And the sine of pi over 3 is root 3 over 2, which is 0.87. And I'm going to take pi over 2. And the cosine of pi over 2 is 0, and the sine is 1. So far, that's my initial point, starting point right there. And graphing these other points, and it looks like I'm getting a circular pattern. And in fact, I am getting a circular pattern because if you think about trigonometry and what your definitions of cos and sine are, remember, cosine is the x-coordinate on a unit circle, and sine is the y-coordinate. And so if I keep plotting points here, and I'm not going to do as many as I did for quadrant 1, but if I go to pi, cosine of pi we know is -1 and sine is 0. So I'm going to have this point eventually, and I think you can see if I did a bunch of points in between, I'd be getting values with opposite x-coordinates to those that I had in quadrant 1. So I can copy those over. And so I think you can see connection to trigonometry here, what I'm going to end up with as I keep going is the unit circle. This was both the starting and terminal point. So I can define a circle with parametric equations in terms of cosine sine. Let's see if we can convert those parametric equations into Cartesian form. Alright, so I have from above that x is cosine t and y is sine t. Now instead of isolating for t, what I'm going to click into here instead is a relationship I know in which cosine squared t plus sine squared t is 1. We know that. And so all we need to do is replace x for cos and y for sine, and we get our familiar equation of the circle. So parametric equations involving sine or cos are often going to produce results that are circular in nature. Let's put this in the calculator. 0 to 2 pi is my range for my parameter t. Our x, I'm just going to set it at -5 to 5 for both the x and the y. And the orientation was counterclockwise in the graphing. So what would you expect to happen if you had your coordinates to be x to be 3 cos t and y to be 2 sine t? So if t was 0, your cosine of 0 is 1 times 3 is 3, and your sine is sine of 0, which is 0 times 2, which is 0. At pi over 2, 90, cosine of pi over 2 is 0 times 3 is 0. And for sine of pi over 2 would be 1 times 2 would be 2. In other words, the points, it's going to be circular in nature, but your x-intercepts are going to be out 3 times as far and your y-intercepts out 2 times as far as before. And so we get a stretch circle, which we call an ellipse. And the direction of graphing orientation is this way, because we started here and the points came in that direction. Now in terms of coming up with the Cartesian form of this equation, what I'm going to do is when I have x equals 3 cos t, I'm going to write that as x over 3 is cos t. And for y over 2 equals sine t. And then I'm going to use, again, the idea that cos squared plus sine squared is 1. But in place of cos squared, I'm putting x over 3 squared. And sine squared will be y over 2 squared. And there you have the stretched equation of a circle. This is like the equation of a circle with a radius of 1 which has been horizontally stretched by a factor of 3 and vertically stretched by a factor of 2. So just to end off, let me just show you some examples of some of the wild shapes that you can get with parametric equations. Parametric equations often, like I said, give you graphs that aren't functions, but they allow you to come up with a much more wider variety of wild graphs than you do typically get with just Cartesian equations. So I've entered my parametric equations here, and let's graph this from -2 pi to 2 pi and see what we get. Alright, some nice patterns going on there. The second one, t cos t and t sine t. What's this going to give us? Okay. Again, you can restrict that by changing the range of the parameter, etc. Okay, and the last example, all sorts of cool patterns you can come up with parametric equations.